Hello, good evening. Hello, good afternoon, everyone. Good afternoon, everyone. I welcome all of you to YouTube channel of Gradeup. All of you, please join for. I hope I'm audible to all of you. Please share it and join as soon as possible. We'll start now. So I hope exam is very near and you all are preparing well, staying safe. The most important point is that please don't get panic. Hello, hello Atulya Swamiji. Yeah, but there were constraints from time. So okay, let us start now. Hello Aman, Shubhadeep, Sai. I welcome all of you. Here we go. So most expected questions. This is my small introduction. Those who have not joined me yet in a Telegram channel, you can join. And if you have any queries or questions, you can ask there at any time. There is a Vision 2022 and for 2023 batches are going on. You can join there. These are the star faculty of the Gradeup. Here is the first question for you. For a soil sample, arrange the following in increasing order. Can you arrange this? Can you tell me which one will be correct one here? If you arrange all this in increasing order, what will be the correct answer here? What will be the correct answer here? So if you are going to arrange in increasing order, the lowest one is nothing but your dry one, right? Then the bulk unit weight will come between your saturated and the lowest one is here already. There is submerged one. Submerged one is already also here. This is the lowest one. Then bulk will come between dry and saturated. So first is your submerged. First one will be your submerged, that is 2. So either C or D. Then after submerged it will be dry, that is 3. So it is obvious, very obvious. Yes, submerged is the lowest one, and from there you will start. And the highest one is what? The unit weight of solid, right? The true and apparent specific gravity of the fully saturated soil is 2.7. And 2. The void ratio will be, what will be the answer here? So true. For this type of problem, actually you should know what is the meaning of true and apparent specific gravity. So the apparent specific gravity is nothing but unit weight of the soil taken at any time. That will vary with respect to the unit weight of water, right? Now he has said that the fully saturated soil, if I'm saying that apparent specific gravity for the fully saturated soil, it means during the time of unit weight calculation, the soil is fully saturated. So unit weight of saturated, if you will take, it will become 2. So apparent specific gravity is 2, that means gamma saturate by gamma W is 2. But this gamma saturate will vary from gamma to, that is gamma D, to gamma saturate. It may be of any value, it may be of any value, isn't it? Now from here you can calculate the gamma saturate. If you will consider gamma W as 1, you will get that is 2, and the true specific gravity already is given, that is G, right? Now from here you got the gamma saturate value. Using the gamma saturate, you can use the formula to calculate the gamma saturate, which is G plus ES, and S will become 1. So G plus E by 1 plus E multiplied by gamma W. Now here once again you have gamma W 1, gamma saturate is 2, and G will become 2.7, that is the true one. Wherever you are using in the formula, it is true only. Then plus E divided by 1 plus E, isn't it? So 1 plus E will be equals to twice of 1 plus E will be 2.7 plus E. So here it will be 2E minus E. So E will become 4.7 minus 2 minus 2 minus 2.7, 0.7. So it will be 0.7. That's all. That's all, isn't it? If the volume of void is equal to the volume of solids in a soil mass, then values of porosity and void ratio respectively are. What will be the volume of solid values of porosity and void ratio? Volume of void is equal to the volume of solid. So if you remember the formula for void ratio and value of gamma W, value of gamma W, you see it is actually in soil mechanics, you are absolutely correct. Gamma generally we are representing with 1 kilonewton, right? Maybe the notations you change it to density instead of the gamma. Gamma is unit weight, right? If I have taken as 1 gram per cc, of course this is density I'm talking about. So sometimes we used to do, as a soil mechanics person, we used to do that instead of gamma we are writing down the raw value. But unit must be compatible, both sides. Whatever you are using the unit, that must be compatible. That must be compatible. Now here, what is the value of your porosity and void ratio is the volume of void. And so if the volume of void is equals to volume of solid, what is the definition of void ratio? Volume of void by volume of solid, isn't it? And what is the definition of porosity? So definition of porosity is nothing but volume of void by total volume, isn't it? Volume of void by total volume. Now what is the values of porosity and void ratio he is asking. Suppose if these two are same, for the void ratio you will get 1, for the void ratio you will get 1, and for the porosity total volume will be double of that, so it will become 0.5. So it will be 1 and 0.5, which is nothing but D, isn't it? The moisture content in a soil sample is 18.2% and the specific gravity of soil particles is given by 2.65. What is the void ratio for sample if the soil is fully saturated? B होगा? क्या बोल रहे हो? If the volume of void is equal to volume of solid, so volume of void अगर volume of solid के बराबर, if it is same, what is the definition? How you are saying that volume of void and volume of solid? What is the definition of your void ratio? What is the definition of your void ratio? Okay, that in that sense, then the value. Okay. I'm sorry. In that sense, you are asking the value of porosity and okay. I got it. Value of porosity he asked earlier, so it will be 0.5 and 1. If it is not given 0.5 and 1, let us consider maybe he is asking first void ratio and then porosity. You are absolutely fine in that aspect. But yes, porosity is 0.5 and void ratio is 1. And void ratio is 1. Just reverse the order, that's all. The moisture content in a soil sample is 18.2%. Specific gravity of the soil is given by 2.65. So W, that water content is given as 18.2%, and the degree specific gravity has been given as 2.65. What is the void ratio for sample if the soil is fully saturated? Once the soil is fully saturated, he is asking about gamma sat is G plus ES. S is 1 divided by 1 plus E into gamma W. Now, if you want to use here, he is asking the void ratio. G is given, gamma saturate is not given at all. You can calculate from ES equals to WG. So, no, not needed. No, the moisture content in from here also, if you want to calculate, W is given, G is given, S is 1. Why we will use this one? ES equal to WG. Directly void ratio can be calculated. S will become 1, isn't it? The water content is given as 0.182 multiplied by 2.65. How much you are getting now? How much you are getting from here? Yes, there is no need to using that equation at all. 0.482. That's all. Now curve for the volume. See, can you see this diagram? Curve for volume change and pore pressure variation is given with axial strain. With the axial strain, which of the following is correct? Which of the following is correct here? This is your option A, this is your option B, and this is C, and this is your option D. Which of the option is correct here? You can see here, due to the axial strain, the change in volume and change in pore water pressure has been given with the curve. Now you have to understand normally consolidated and over consolidated soil, right? Normally consolidated and over consolidated. You know that already. For over consolidated must be treated like a dense soil. Over consolidated is like a dense soil. And for the dense soil, the packing is slightly different. For the dense soil, we assume that the green packings will be too much intact, right? Too much intact. Now, if you are going to apply the force, or if some axial strain will happen, due to the axial strain, suppose if you consider this as first layer, this as a second layer, what will happen? There will be a slippage between these two layers. If there is a slippage between these two layers, the void is going to open up for a small amount. Are you getting my point? The void is going to open up because this is the initial condition when it is too much intact or when it is too much dense. Density is high. Now in the next stage, when you are applying the force, if the axial strain will happen, next stage you can understand that. See, just for the representation purpose, I am drawing this diagram. Now this is the new condition when the particle grains will slip over each other. A volume of the void will actually increase little bit, the slightly increment of the void. Due to the increment of the void, now overall volume of the soil will get increased. Overall volume of the soil will be increased. Are you able to understand that? Very necessary concept. Now imagine that this I am talking about the dense soil. Whenever I am talking this about dense soil, it is nothing but your over consolidated soil. Now you see the change in volume I am talking about. The first curve is something where you are increasing the axial strain. The strain, if you are increasing the axial strain here, with the axial strain increment, how the volume increases, that is how the volume will be increased. Slightly initially a little bit down, that reduction in the volume, but later on, due to the slippage and readjustment of the particle, they don't have any space here, the little bit increment of the volume will be observed only in the dense soil or over consolidated. So this is the over consolidated, and here for the normal consolidated soil, it is a normal soil. Just try to assume that the particles, soil grain particles, are kept quite away. They are just in a comfortable zone. If you are simply providing the axial strain, what will happen? They will intact to each other. They will come close to each other. So by that what will happen? Actually, the reduction of the volume will be seen throughout. So that is what you can see here for the diagram number 2, curve number 2. If you are increasing the axial strain, a continuous reduction in the volume is happening. A continuous reduction will be observed. But here also, after some time, the reduction of the it is not the intensity of the increment, the way it is reducing the volume is not same everywhere. As long as you are increasing the axial strain, the increment or the reduction of the volume get decreases, right? Now coming to the next one, that is pore pressure part. Pore pressure. Now you imagine that between these grains, when the particle are in a dense position, when the soil is under dense condition, when the soil is under dense condition, these are the void where water is present. Imagine that instead of some water, just for imagination, some honey or some viscous material, highly viscous material, which you can feel it. Now due to sliding of these particles, what will happen? There is a slight increment of the volume of the void. If there is a slight increment of the volume of the void, what will happen actually? If it is a viscous material, if little bit of the volume get increases, suddenly a tension will occur in the water zone. Suddenly a tension will occur in the water zone. So the pore pressure actually get reduces due to the axial strain. Are you able to understand this point? If you are providing the axial strain here, the volume actually increases, the void of the volume of the void, and due to increment of the volume of the void, just you can imagine that take the honey between the two plates, right? Between two plates, you take the honey and try to imagine the concept which I'm explaining it right now. Now suppose if you have kept honey, if suppose you are pressing it a little bit amount, if you are pressing it, what will happen? Honey will be under compression. Instead, suppose if you are displacing, if you are just translating this upper plate a little bit upward, only very small amount, little bit upward, honey will be under tension, isn't it? Are you getting my point? So slight increment of the volume inside will make the fluid under tension. That is why you should understand the pore water pressure also. Pore water pressure also inside the void will be under tension, so it may go negative. That is the very important concept for the dense soil. So for over concentrated soil, the pore water pressure due to the axial strain after some time may go to negative portion, whereas it is not there for the normally consolidated soil. As long as you are pressing it, as long as the axial strain will happen, the pore water pressure continuously increases. That's what. Now you just match it. This is your over consolidated one and this is your normal consolidated, right? So fourth and one is your over consolidated, and these 2 and 3 are yours. So answer is D, absolutely correct. Which of the following here is correct now? Which of the following conditions may generate negative pore water pressure? Which one is correct here? Loading the sample beyond pre-consolidation stress, capillary rise of water in soil, application of load on normally consolidated soil, application of load on over consolidated soil. So 70% of the answer already have given here in the previous slide. 70 to 80% answer already have given in the previous slide. Which of the following condition will rise the negative pore water pressure? That is 100% sure. For the capillary rise, you know that already. If the capillary rise is going to happen, of course the water will be under tension. In a capillary rise, water will be under tension because it is going to hang over there, right? So this is very obvious. Everyone knows that. Now what about the loading the sample beyond pre-consolidation stress? If you are loading the sample beyond pre-consolidation, now once again you understand that application of load on over consolidated soil and loading the sample beyond pre-consolidation stress, actually both the statements are nothing but same. Both the statements are nothing but same. Are you able to understand this? Both the statement, the first statement and the last statement, both are same. You are going to consolidate the soil beyond pre-consolidation stress is nothing but, see, when you are loading over not over consolidated, normally consolidated, both the statements are same. If you are loading any soil sample beyond pre-consolidation, see, if any soil sample has seen suppose a stress of any stress, that is pre-consolidation stress, this is that amount of stress if the soil sample has seen in the past history. Now currently if you have taken the sample and you are loading, if you are loading that particular soil till sigma p is known as your over consolidation stress, and beyond pre consolidation stress if you are loading it, it is nothing but your normally consolidated soil. So application of load on normally consolidated soil and loading sample beyond, both are same, nothing but here it is normal. And just now I told you that for normally consolidated soil you are not doing the negative pore water pressure, it is there only for the over consolidated soil. So answer will be here your second and fourth. The pore water pressure in the soil sample of consolidated test is pore water pressure in the soil sample in a consolidated test for single drainage. Single drainage. What will be the pore water pressure? Generally single drainage if you are providing at the top, then the pore water pressure will be maximum at the bottom. How it varies? If you are providing the drainage gallery to the top, the maximum pore water pressure will be there at the bottom. That is the variation of the pore water pressure. Sometimes if you are providing the drainage both side, if you are providing the drainage at the top and as well as at the bottom, the pore water pressure will be maximum at the mid. Remember that one. That's all. The clay deposit of thickness 10 cm and void ratio 0.5 undergoes settlement, and now its final void ratio is 0.2. The thickness of the settlement layer. Thickness of the settlement layer will be what? How much? What will be thickness of the This is simple. Deposit of 10 cm void ratio 0.5 undergoes for the settlement. So delta H by H naught, the initial thickness, must be equals to, with respect to the void ratio, it is nothing but delta E by 1 plus E naught, isn't it? The clay deposit of 10 cm and void ratio given as 0.5 undergoes for the settlement, right? And now its final void ratio is given. So delta E already you know that is 0.3 and the initial void ratio was 0.5, right? And the thickness given for the soil is 10 centimeter, right? So delta H, how much it will become? Simply you calculate in terms of centimeter, it will be 0.3 by 1.5, it is 2, and it is 10 by 2, it is 5. Just a second. Thickness is 10, and he's asking what the clear division of settlement of the, now it's one, the thickness of the clay deposit thickness is 10 cm and void issues is undergo settlement, and now it's bandwidth the thickness of the settlement layer. Yes, that's okay. So 10 into 0.3 by 1.5. So I think some problem with the option, no? It is in 10 centimeters, so correct. No, this will be no. Okay. So, I'm sorry. 3 5 15 5 2 10. ठीक. My mistake. If the coefficient of permeability is doubled and the coefficient of volume compressibility is halved, the coefficient of consolidation will be. If the coefficient of permeability is doubled, and then what will be the coefficient of there is a small relation for this one. If the coefficient of permeability, then gamma W CV, coefficient of consolidation, what will be the answer for this one? CV equals to K by mv gamma w, right? Cv is equal to mv, Cv is equal to K by mv gamma w. No, Cv equals to K by mv gamma w. Now if the coefficient of permeability is doubled, if the K will get doubled, right, and coefficient of volume compressibility, this is mv coefficient of volume compressibility, if it is getting halved, so what will happen? What is the new change you will find? That is mv, mv and gamma w. So this half will go up and it will become 4 times. Now what about this one? A masonry dam has a pervious sand as a foundation. Find the maximum permissible upward gradient for the factor of safety 4. This is very simple problem. Only you need to know what is the critical gradient, that is g minus 1 by 1 plus e. Once you can calculate the critical gradient, just divided by factor of safety, right? That is the permissible upward gradient. So that is given 2.65 minus 1 divided by 1 plus the, they have given porosity, just you calculate the void ratio. Void ratio must be calculated. So your void ratio will become 0.45 by 1 minus 0.45 and it will be 0.818, right? It is around 0.9, then divided by whatever you are getting it from here, that is 0.907 something. Just that is the critical hydraulic gradient. If the factor of safety he has asked about 4, then what will be the permissible one divided by 4? Divide this critical hydraulic gradient by 4 and you will get the answer which is nearby this value, isn't it? Now what about this one? Which of the following is showing the correct relationship for the liquidity index? Which one is correct here? So for this you need to remember the liquidity index, plasticity index, consistency index, toughness index, flow index, all the relations. If you will remember, then it will be very easy for and convenient for you to answer this type of question, isn't it? This is slightly amazing that you are saying the answer is A. How it will be A? It is the answer C. Here you have WL minus WP. If it is correct, then WL minus WP divided by IP is also WL minus WP. It will become 1. Then what is the meaning of writing down this relationship? Right. Now which of the following are correct here? In a Cassegrain test, liquid limit is the water content corresponds to 25 number of blow. 25 number of blow. And so first one is correct now. That's what we are doing here to find out the liquid limit. Plastic limit for the soil is at which one make the thread of 3 mm. That is also correct. Flow index tells the rate of loss in a shear strength upon increase in water content. Increase in water content from the liquid limit test. What the graph you are getting it for the for any of the soil sample. If you are just increasing the water content, the number of blow requirement went down, right? Now this is the criteria by which one can understand. Suppose if you have a two different slope for the two different soil, two different slope if you have for two different soil, if you have a slope steeper or maybe lesser, so based on the slope, that slope reflects that slope we are actually how we are representing, that is our nothing but flow index, right? Slope of this line is we are calling it as flow index. Now with the help of the flow index one can identify how the shear strength of the soil how it is losing. If you say for the steeper one, you can say that just for the small increment of the water content, if you are increasing out, the strength of the soil get lost very, for the shorter amount of increment of water content. That's also tells by this slope. So yes, this is correct one only. Flow index tells you how the loss of shear strength will happen due to increment of the water content. So all are correct here. Then excuse me, I'm sorry. T or not visible. 1 second. Okay. The soil with zero plasticity index represents, it is non-plastic. If any soil, as per this diagram also, if you'll understand, it is very easy to understand, right? This is your change in volume, this is your change in volume, and this is your water content. Now we said that the soil which is this is your shrinkage limit, means saturated, fully saturated one. This is solid and this is semi-solid, and then you have a plastic and liquid. This is your plastic limit of water content and this is your liquid limit of water content. If I'll say that the plasticity index is 0, that means IP is WL minus WP is 0. If WL minus WP is 0, means I'm saying that there is no zone of plastic. That's all. If you do not have that value of IP, if you do not have the value of IP, that means the soil is not at all plastic. No more plastic at all. For a liquidity index greater than 1, it can be said that if the liquidity index is more than 1, then what one can interpret it from there. What is the interpretation? Just now I told you that if IL, you have already a formula that W minus, what was the formula for that one? For liquidity index, okay. Now if it is greater than 1, what does it mean? How, when it will be greater? This is your natural water content. This W is your natural water content. Just now we have seen in the previous slide. If water content is more than liquid limit, if natural water content of the soil is more than the liquid limit, then only this will become more than 1. If it is more than 100% sure, it is now this is your WL. So if WL is more than this, natural water content is more than WL, that is 100% sure it is more than 1, and more than 1 means you have a liquid state. You have a liquid state. Did you get that? When the compactive effort is increases in the standard compaction test, the optimum moisture content, what will happen to the optimum moisture content if the compactive effort will be increased? For unit weight versus water content, if you are compacting it, you have a, at any optimum moisture content, at any water content, actually you have a maximum dry density. Now that dry density maximum, what you are getting, we are calling it as optimum moisture content, OMC. This is nothing but the water content. This is nothing but the water content at which you will get the maximum dry density of the soil. Now if you are going to increase the effort, what will happen? Means you are using the higher energy to compact the soil. If you are using the higher energy, then mobilizing, so for the mobilization of the soil, whatever the water content was needed, the small water content, so that the soil grains can slip over each other to get the maximum density. Even if you have a less water content compared to the optimum moisture content which you got earlier, if you are providing more effort or more energy to compact the soil, then what will happen? One thing is that sure, you will get the dry density at lower optimum moisture content or at lower water content. And obvious that if you are using the higher effort, higher dry density will be achieved. Higher dry density will be achieved. So these two are correct here. And what he's asking, competitive increase in standard content, that's optimum moisture content. Optimum moisture content actually decreases, right? According to Skempton's formula for a surface footing of square shape, the net ultimate bearing capacity on a purely cohesive soil of cohesion C. As per the Skempton, as per the Skempton, what is the value of net ultimate bearing capacity? So first of all, net bearing capacity for a cohesive soil, the net bearing capacity. See, bearing capacity formula, bearing capacity equation, if you'll see here, ultimate bearing capacity equation, you have a CNC plus gamma dnq plus 0.5 or whatever gamma b and gamma. This was for strip footing. Now it is for cohesive soil. For cohesive soil, n gamma is 0, so just neglect this one. And net ultimate means once again you have a qu minus gamma d. Now if it is qu minus gamma d, finally nq is also 1, so you will get only CNC. Now net ultimate for a cohesive soil is your CNC, and Skempton actually gave the equation for cohesive soil only. So the NC value for the Skempton, and he's saying that for square one, for the square and circular, for both square and circular, he has given an equation which is nothing but 6 into 1 plus 0.2 df by, with respect to depth of the footing and width of the footing, df by b. And this is only for circle and square. This is only for circle and square. Now NC value, how much it will be? For a surface footing, means if you are going to keep the footing over the surface, this df by b ratio will become 0. If df by b ratio will become 0, you will get simply 6. Remember that NC value maximum also, this is the minimum value of Skempton's, where you are getting the 6C. But what is the value for Tarjagi? That is 5.7, right? 5.7. And what is the value for Prandtl? That is, I think, 5.13. One more thing you remember, that if your depth by width, now width of the footing will be constant, you may achieve more and more depth. What is the maximum value of NC you have? What will be the maximum value of NC you have? So it has been restricted to df by b when it is greater than or equal to 2.5. Correct, no? 2.5 25 50 for 1.5. हाँ सही. Now if it is the greater than the df by b ratio, if it is equal to or greater than 2.5, that is the maximum 9 you will get. So value of NC will vary from 6 to 9 for Skempton. That you keep in your head, it will be easy. And one more thing, you remember that for the footing purpose and all, you are using that 9C. For the pile foundation, when you are using the numericals, you are using that 9C value. Why? Because the depth of the footing is more than see, the ratio of the df by b there is more than 2.5, quite large, too much more than 2.5. So there we are using the Skempton's value. A 2 meter wide strip footing rests on a depth of 2 meter below ground surface in a clay deposit where water table is at ground surface. Okay, the best estimate the net ultimate load which footing can carry is. What is the net ultimate load the footing can carry here? A 2 meter wide strip footing rests at the depth of 2 meter below ground surface. 2 meter below ground surface, right? Despite where the water table at deposit, where the water table is at ground surface only. Here only ground surface. At ground surface you have a water table. C value they have given gamma C. The best estimate of the net ultimate load which footing can carry. What will be the load that footing can carry? Can you calculate this one? Can you calculate this one? How you can calculate this one? This is your first of all clay deposit. For the clay deposit, the net ultimate he is asking, the net ultimate. What will be the net ultimate bearing capacity of the soil. Net ultimate bearing capacity will be nothing but only C and C, right? C and C. And here C and C will become how much? C and C net ultimate C is given as 3, and NC value already for the Terjegi one we are considering as 5.C. One more thing, it is for strip footing, so I am not taking care of any of the factors, shape factor here. So it is only 5.7 into 3. Now the answer has given in the term of the best estimate of the net ultimate load, right? Ton per meter. So तो 15 और 15 15 17 17.1 17.1 ton per meter square is your bearing capacity of the soil, right? 17.1 ton meter square will be your bearing capacity of soil. Now multiply this one with the 2 meter wide strip. With the 2 meter wide strip, if you have a strip of 2 meter wide, he has not given in terms of square, he has given in terms of ton per meter length, so divided by, multiply with by 2 meter of the length, so that you will get the 34.2 ton. This is per meter, 34.2 ton per meter. That is how you should be representing it, right? Yes, C is your answer. The net ultimate bearing different. Okay, the net ultimate bearing capacity of soil is 25 ton per meter square and density is 1.7 ton per meter cube. The safe bearing capacity at 1 meter below the ground surface, right? Factor of safety also is given here. He is asking about safe bearing capacity. How you will calculate the safe? So he has given the net ultimate one, that is QNU. Directly he has given. From the QNU you can calculate the QNS, right? So QNS will be simply QNU by factor of safety, which is 2.5, and you will get 25 by 2.5, so you will get 10. Now this is your QNS, net safe. What is the safe bearing capacity? Q safe will be simply QNS plus gamma D, right? Now this is 10 plus, and gamma D will be, gamma is given here, that is 1.7, and D is given as 1 meter below the ground, so it will become how much? 11.7. In the case of pile foundation, negative skin friction may occur at a load which is, it may occur at a load which is, see, there's, what is your negative skin friction during the pile foundation? If some of the portion of the soil, if it is going down, maybe just just take the diagram this side. Suppose this is your pile, right? If some portion of the soil, if it is going down, and the relative velocity of the soil, if it is more than your driving pile, what will happen? The soil will drag the pile downward side. You are actually expecting the upward skin friction. You are expecting the upward skin friction to hold your load, but due to the downward movement of the soil, as the soil is dragging the pile downward, you are going to get the skin friction downward side. But it is not at all something like, ki bhai, what will be the magnitude of the load? It depends on your soil strata, the condition of the soil also. There are so many things which depends. It's not about at any magnitude you may get. At any magnitude, whether lower or higher, we cannot say that. At any magnitude you will get. A square pile of section 30 by 30 centimeter length 10 meter penetrates a deposit of clay having C equals to 5 kilonewton per meter square and mobilizing factor is given 0.8. What is the load carried by the pile by skin friction only? So for the skin friction, if it is single pile, you know that mobilizing factor will be needed or adhesive factor will be needed, right? Sometimes it is known, they are saying it as adhesive factor or mobilizing factor. So first of all, calculate what is the, 0.8 is your mobilizing factor, and that C value also is given. That must be first of all multiplied with, this is the total cohesive force you are going to get, multiply with the total area of the pile. If it is a square pile, of course, for the square pile, the total area, the total skin area, all the four side will be how much? This simply 30 into 10 meter is the length and 30 centimeters. So 10 into 0.3 meter is your multiplied by 4 is your total area, isn't it? 10 is the length, 0.3 in terms of meter is the width. So 10 into 0.3 into 4 total area. Multiply this, how much you are going to get here? Kitna aega? How much you will get it here? 48 kilonewton, right? 4 12 12 25 8 48 48 kilonewton. Two circular footing of diameter d1 and d2 are resting on a surface of purely cohesive soil. The ratio d1 by d2 equals to 2 if the ultimate load carrying capacity of the footing of diameter d1 is 200 kilonewton per meter square. Then the ultimate bearing capacity of the footing of diameter d2 will be, of the diameter d2 will be, yes, see, as long as two circular footing are kept resting on the surface of the purely cohesive soil. For purely cohesive soil, just now I told you, he's asking about ultimate bearing capacity. So ultimate bearing capacity will become CNC plus gamma d NQ. Even though NQ will become 1, you have a CNC plus gamma d, right? Now gamma d is what? Depth of the footing. If you are keeping the two footing over the surface directly, there is no depth, so d also, this will also become 0. Now the ultimate bearing capacity of the soil clearly depends on simply the C and NC value, right? C and NC value, whatever the ratio of the footing you are going to take, that doesn't matter at all, and whatever the value of QU was there for the D1 diameter or D1 footing, same will be there available for D2 also. Whatever you use the diameter, that does not matter here. Which of the following statement is not correct for the bearing capacity of shallow foundation here? For bearing capacity of shallow foundation, if you see, the ultimate bearing capacity is well defined for general shear failure. Now this one is quite informative but good and easy also to remember. This is your load and this is your settlement. Now load versus settlement curve, if you remember, you will be able to easily identify that one. Always remember this one, this is quite helpful. This is the load versus settlement curve for general shear failure, and then you have a local shear failure, and then you have a punching shear failure. It is quite obvious that for the punching shear failure, large settlement will be occurred, isn't it? So this is the diagram. If you are increasing the loads, directly the so much of settlement will be observed for the local shear failure. I will write it down here also. But if you observe for the general shear, this one is for general shear failure. General shear failure. Now see here, only for the general shear failure, the ultimate load carrying capacity is well defined. It is well defined. Because this is a kind of, it is going to happen only for the generally for the dense soil. If you have a dense soil, then only you can expect a general shear failure, right? And for the dense soil, one should understand you have an interlocking of the, see, the shear strength of the soil comes from the interlocking as well as the friction and cohesion, all right. Now if it is dense sand, if I'm saying that, suppose cohesion, I'm just ignoring, no cohesion, not ignoring, it is no cohesion at all. Now only the total shear strength available will be only due to the interlocking and friction between the particles. If you are applying the load, what will happen? If once the interlocking will get break, there will be normal slippage of the particles. So that is the point one can say that where the interlocking is getting break and sudden decrement of the load will be observed. The way you are observing it for the for the mild steel tensile test when there is a upper yield to lower yield. It is coming from upper to lower yield because of the structural failure, which we generally refers as the carbon slippage from this point to this point may be happening inside the material. It is your material science that you can correlate a little bit from your failure of failure of your dense soil, dense sand. So it is correct one only. The ultimate bearing capacity is well defined for the general shear failure. Meyerhoff has considered the failure plane till ground level. Yes, that is also true. The Terjagi, when he considered, he actually said that he is considering the general shear failure, but the failure plane has not been considered till the ground surface. So what he did that the failure plane, as per the Terjagi, he has only considered till the level of footing, when afterwards the Meyerhoff has considered it till the level of ground. That is also correct. Skempton did not analyze for cohesive soil. That is totally wrong. Just now I told you Skempton did the analysis for cohesive soil only. And tilting and large settlement can be observed in local shear failure. He was asking which one. Tilting and large settlement can be observed in local shear failure. Oh, then I think this has become some. Tilting and large settlement can observe. This is also tilting and large settlement can observe. So the option has become in such a way that it will be difficult for you to identify which one is not correct here, because first see, Skempton did the analysis for. Oh, he did the analysis for cohesive soil. I'm sorry. How I read that he did not did the analysis. He has not completed the analysis. This is also correct. I'm sorry. Just now we have seen Skempton did the analysis for cohesive soil. Tilting and large settlement can be observed in local shear failure. You cannot observe the large settlement. Large settlement will be observed only for punching shear failure, and tilting will be observed only for general shear failure. In a local shear failure, it is actually not that much possible to find out whether the tilting, not too much of tilting, not too much of general large settlement. Now, which of the statement here is correct? Adhesive factor for load carrying capacity of group of pile is 1. Providing the sand drains, which of the statement is not correct? He is asking. Not correct. Adhesive factor for load carrying capacity of group of pile is 1. Yes, for the group of pile, the adhesive factor is obviously 1, because when you are considering the group of pile, there is only all the skin area, all around. When you are considering the block failure, it is the interaction between soil to soil. So there is no need to take the mobilizing factor or adhesive factor. So that is why this we are considering as 1. That is obviously correct. Then next one is your providing the sand drains will increase the settlement of pile. It will not increase the settlement of pile. It will increase the time of settlement. Just right. It is simply once again from the consolidation itself. Even though if you will provide the sand drains, extra sand drains, so drainage area, whatever you provide in the soil will actually accelerate the settlement procedure, which will all the settlement will be occurred only at the lesser time period. But the total ultimate settlement, you cannot increase it by providing more drainage, right? By providing the sand drains, it will not increase the settlement of pile. Only it will increase the rate of settlement of pile. Fender pile is used in harbor, and the pile which takes lateral load known as batter pile. That is also correct. You know that fender we are using it in harbor dock. In a harbor dock, actually, when the ship comes, it hits the dock. Even though at a very low speed, it has a very high, very huge weight. So momentum is quite high. If it will hit the dock, will get damage. So to stop that, actually we are using another material which will absorb the energy. That we are calling it as fender. Sometimes instead of the fender, we are using the fender pile here also, right? So fender pile, we are using it just to absorb the impact energy. And yes, batter pile you are using it for the taking lateral loads. Minimum spacing between pile group of the pile is around 3 to diameter of the pile. That is also correct. So this is the only statement which is not correct, the B. The water table at location is that ground surface and saturated unit weight of soil is 20 kN per meter square. If due to heavy precipitation, the water table is at ground surface, right? And due to the heavy precipitation, the water level rises by 2 meter above the ground level. If the water table rises by above than ground level, the increase in the vertical effective stress at a point 2 meter below the ground surface. What will be the answer for this one? You remember, for whatever the people will be asking this type of question, always remember what he's asking, that water table already you have at ground surface, right? Water table already you have at ground surface. Already you have at ground surface. Now from the ground surface there is a rise of water table, and after some time what he's saying, that initially when the water table is at ground surface, maybe at 2 meter deep from the ground, from the level of the ground at 2 meter depth, there was some stress due to rise of the water table. If the water table rises, what will be the what is asking, increase in vertical effective stress. Increase in vertical effective stress. So only due to the rise of water, only the total stress will get changed. The effective stress does not get changed at all. Remember that one. So whatever the question will be, always remember, if the water rises above the groundwater, above the ground level, if the water rises above the ground level, you can just calculate and understand it, that effective stress is nothing but your total stress minus pore water pressure. If you do that for these two different situations, you will find that. And also always remember, above the ground surface, whatever the rise or fall of the water will happen, above the ground surface, whatever the rise or fall of the groundwater will happen, the water level will happen, that is not going to affect your effective stress. That is not going to affect your effective stress. It will be zero only. I'm really sorry, actually that is how I have to end it here. That's all for today. I need to end it up here, that's all, right? Thank you all of you. Thank you everyone. All the PDF which I have taken, I will be providing in my Telegram channel. Please take care.